Hi, the IoT idea that we are going to talk about today is a smart connected world with IoT. We are now living in a fast changing world where our environment is becoming smarter day by day. The devices we are using are becoming more and more enabled and making us much more connected than ever before. Smart city is a very diverse concept. If we take our office space or hotel buildings, for example, they are quite complex as well. There are multitude of services that are part of building infrastructure these days. Enabling all these services to be internet aware and converging them to provide a connected experience is what we can imagine in the smart cities of future. Our vision is to provide a connected backbone infrastructure for buildings using which we can enable intelligent management of the building resources and provide smart services to its users. Here, we will be talking about probably the most important resource in a building space, that is, our elevators. And using Cisco technologies and sensors from RelayR, we will enable the existing legacy elevator infrastructure and transform them into smarter elevators without any modification in the existing hardware, and all this can be possible without any major investment. We will talk here about the challenges that are usually faced by users in office spaces. With poorly planned elevators, user experience can get impacted. We all work in fancy high-rises office spaces, but that fun comes with problems. How many times have you been in a situation where you are in a hurry for a meeting and you barely catch an elevator in the lobby only to know that there are 10 guys in the elevator who will all get off before you and you can just wait and watch? That's no fun. Most of us don't even realize, but the elevators are the major contributors to the electricity consumption in a building space. Elevators may consume 72% of the total electricity built, and non-optimal usage may cause premature breakdowns and thus heavy bills for the costly equipment replacements. As per case studies from major cities in the United States, an average office goer in New York may spend 22.5 hours only to wait for an elevator in a year on an average. Other cities like LA and Chicago are fine behind with figures for like 13 and 12 hours respectively. We collected sample data from studies with which we can conclude that if we know beforehand the user's destination with the elevator, we can save around 50% of the wait time and travel time for the user in an elevator. Time is money and is of essence today, and we aim at saving this time through our IoT idea. We have created a smart application that uses various Cisco technologies like Meraki location-based CMX APIs, Spark, Tropo, Zeus, and Shipt, along with the sensors from RelayR and RelayR Cloud to create an intelligent application which learns your usage patterns with time. The usage can mostly be very much predictable in an office or residential building. As elevator lobby area, the application understands your usage, your location, and based on your location, it can sense your need of an elevator. It can also acknowledge the usage patterns of others who are already waiting in the elevator lobby and hence can prompt you the best suitable lift for you in real time through Spark. The user also has the option to request for an elevator for a specific floor through the application to know of the best elevator to use. The building administrator can also learn the usage statistics that can be provided from the dashboard, like total usage of each elevator, which floors are used more, with which better elevator management can be planned and proactive maintenance can be scheduled. We are using Meraki CMX location-based APIs to get the real-time user data to our backend application with which we can learn a user's pattern. We use Spark as a means of interaction with the smart application for the user and for the building administrator. Via Tropo, we provide a means of communication for the building administrator as well, where the application can inform about any major or minor faults in the elevator via text or call to all those who have registered. Via Zeus, we are maintaining the historical data for statistical analysis, and Shift is being used for staging the application. The sensors from RelayR can be used to proactively understand any issues in the elevator like sudden jerks or faulty lights or alarms. And the application can directly call or text the administrator to inform about the problem observed. So now, when you are about to enter the elevator lobby and you always travel to your office on floor 15, and there are 5 users already in the lobby area who go from floor 3 to 6, the application will prompt you to use elevator 2 instead of elevator 1 that has been already scheduled for other 5 users. That will save a lot of your time. With such a system, the administrator can also plan optimal usage of all the elevators. They can also plan to impose time-saving algorithm during the heavy morning or evening hours, and cost-optimizing algorithms can be applied during the non-busy hours of the day, hence maintaining the equipment better and drastically improving user experience as well. All of this can be driven just by the statistical data that we have collected and provided on the dashboard. Now we'll head for the demo of the application. This is the test hardware that we are using for this demo. We have 4 Meraki access points. We have sensors from RelayR, which are luminosity, noise, and temperature sensors. We have a test phone on which a user will get text or call alerts via Tropo for any major or minor issues. And we have Spark running on the laptop and this test phone as well for the users. This is the user onboarding process where this web page gets pushed directly from the Meraki access points onto the user's device. Here the user has to provide his Spark credentials and also provide the MAC address of the device on which he is using this application. If you don't have any Spark ID already created, it takes you to a Spark page to create a new one. Then you hit a submit, and from now on we start monitoring this MAC address. This web page is a responsive page and works well on mobile devices as well. This is how our application fits with the Meraki architecture. The Meraki access points keep sensing the mobile devices in the vicinity and sends that data at real time into the Meraki cloud. The Meraki cloud sends that cumulative data to our application, which is registered. This data holds the access point and the client MAC details. And with this data, we start creating the usage patterns. This is how the Meraki dashboard looks like. It's very powerful. It provides all the users which are connected to the access point network, all the visitors and the passers-by. This is the map view of all the 4 Meraki access points in our network, geographically located very nearby. We can go on to each access point and actually check out all the devices which are connected to that network. For our simulation, we had turned down 3 of our access points to simulate a floor-by-floor scenario. So right now the user is connected to one of the access point. Our application gets the HTTP posts from the Meraki cloud, which holds all of the data of all the devices which are seen in the Meraki network. This data is very powerful, and with this data we start building up our patterns of the user's usage. This is how the Spark interaction with the users and the administrator will look like. We have these 3 Spark accounts set up for all the 3 users, and the bottom left you'll see the Spark account for the building administrator. Now, as soon as the users are sensed by Meraki endpoints, the Spark rooms get created. The administrator has his own room, plus he has a room with all the users as well. As you can see, the building administrator room has the 2 administrators, and the other rooms have one of the users and one is the administrator himself. We provide commands for the users to interact with the application. The users can type in help and they'll get the set of commands that are applicable. The administrator has his own commands as well. The administrator gets the option of choosing the better algorithm based on the data that we have provided him. During the busy hours of the day, he can set the algorithm to have time optimization. Once he sets that, the user will get an appropriate lift once the user requests a particular lift. Similarly, the administrator can choose cost-optimized algorithm during the non-busy hours of the day. Once he sets that, you'll see the response of the application to the user on lift requirement changes. Now a user can also update his regular floor. Let's say, for example, his usage changes during the time and his floor changes. This is how the dashboard on the Zeus will look like. We have actually pushed the data of a user's usage patterns onto the Zeus, with which we can pull out statistical records of the highest used floors. We can pull out the total usage of different elevators, which will help the admin plan his elevator usage. Here is how the administrator has his interaction with Tropo, Spark, and the RelayR sensors. Here you can see the Spark page of the administrator opened up and the test device which has been registered on Tropo. From the RelayR dashboard, you can see the luminosity was fine. Now we are simulating a light out scenario where the luminosity will go down. As a result, the application will send out a text alert via Tropo to the administrator's phone device. It actually reads a minor alert and the lift 2 requires an attention, the light went out. Now here we are simulating a major alert by sounding the alarm. Based on the sensor data, the application will send out a Tropo call to the administrator with the actual message that the alarm has went out in lift number 2. The same message is sent on the Spark page as an urgent attention as well. This was the complete demonstration how we have IoT enabled the existing legacy elevator infrastructure to make it smarter and well connected using Cisco technologies and RelayR sensor data. Thanks for watching.